Somebody asked about 35. We will probably end up doing a circuit with what we're doing today, but not today. I have to teach it to you first. Okay. All right, here's the derivative. It says, find the function. So I'm given the derivative. I'm going backwards. I have to find the antiderivative. I am going to rewrite this, Van. I apologize for getting your text late. I fell asleep last night.
Oh my God, can we just do it?
Okay, we'll just run through it. All right, so it won't take but a second. The derivative here, so I'm going to add 1, and then this is what I'm going to divide by in the front. So I have x to the -1 plus, do not forget that constant c, and I am going to use the point that is given to me, 2, 1. So 1 equals 2 to the -1 plus c to find the value of c here. So this is 1 equals 1/2 plus c. I subtract 1/2 and get 1/2 equals c. So my equation for f of x, and this is not that general equation, but this is a specific equation because I have a point. So f of x is equal to, I come back to this, x to the -1, and I plug in my c that I found. And I'm done. Okay.
Why wouldn't it be, don't you want to calculate?
Whenever.
Wait, what'd you do with the 1/2? Did you divide it?
I subtracted from both sides to solve for, so.
Of 1/x² would be the natural log of.
So natural log, if the x does not have an exponent on it, yes, it would be. So if my derivative was something like 1 over, I don't know, x plus 5, it would be natural log, yes. If it's bigger than an exponent of 1 in the bottom, then you can change it to a negative exponent and use the power property. And if you get confused, if you did it as the natural log, if you went backwards once you found your antiderivative, find the derivative of your antiderivative, you should end up back where you started. And if you don't, you did it wrong. You see what I'm saying? So if you looked at that and went, well, I think that's natural log of x squared. Well, what's the derivative of natural log of x squared? Chain rule, right? Which is not where I started. Right. Which would be 2x over x squared, which is, of course, 2 over x, which is not this. That make sense?
Sure.
What else?
We do
12. 12.
Okay, so when you do.
Oh!
So you do natural log.
Yes. It is. It just. That's what all of those took A rock and related back to I rock. So somebody asked about 11 first, I think, with the speeding, and I talked about it a little bit yesterday, and it's really cool to think about because it actually really does work, Dylan. I bet you could use this with your plane. You could use this thought process with your. Yeah. You were talking.
I don't know how you've done that. It's not my fault.
Huh? There wasn't. Okay, so here's the math I used. If she what? Oh, when I was in the hospital for surgery, they tried to do the IV there, and they blew my vein. 159 miles in 2 hours. So that would mean that it's an average of, what is it? 79.5 miles per hour. Yeah, this is 11. Right. This is the average rate of change. It's the endpoints because they said at the end of the trip, it took 2 hours, traveled 159 miles. So those are the two endpoints, 0, 0, and then 159, 2 hours. And so somewhere in between there, her speed had to hit 79.5 by the MVT. MVT says that the instantaneous, so at one point, instantaneously, her speed had to be that because the average speed was that. So she had to be speeding at least 1 point during that trip. Yeah. Does that make sense? Okay. Number 12. It took 20 seconds for the temperature to rise from 0 degrees to 212 degrees when a thermometer was taken from a freezer and placed in boiling water. Explain why at some point in that interval the mercury was rising at exactly 10.6 degrees Fahrenheit per second. So same thing. The average rate of change is 10.6 degrees per, what is it, seconds? So because the average rate of change is 10.6 degrees per second, at some point, there's an electric one on the thing. Okay. At some point during that interval, it had to hit 10.6 degrees per second by the MVT theorem. That's all you have to do. Yeah.
All right, well, I think 13 is fine because it's the same thing. How about 14?
What about what?
14. Okay, you can divide all these 11, 12, 13, but I didn't know what to do before.
Okay, so 26.2 divided by 2.2 is what?
Oh, I thought it was 2 hours.
2.2 hours. Yeah. So the same thing again.
How do you shove it twice? My mom loved me.
Show that at least twice the marathoner was running exactly 11. No, but I'm. What you say? What is 26.2 divided by 2.2? Well, but it's higher than 11. So if it has to hit 11.9, let's think about this. If it has to hit 11.9 and she's running, she has to speed up to get to 11.9, which means she goes 11 miles an hour. And she has to slow down to get back to stop, right? Does that make sense? Like if this is her average rate of speed, we know she goes at least that fast at some point. So she starts out running, she has to get there. She doesn't instantaneously hit 11.9. So she has to think about it driving in your car when you push the accelerator. If you get up to 60 miles an hour, you pass 55, but before you stop, you have to hit 55 a second time, right? Because you slow down and stop. And she stopped. So she started and stopped. So she had to pass. If she hit 11.9, she had to pass 11 getting there and pass it coming back to stop. Does that make sense?
Yes.
Did I explain that okay? I feel like that was a convoluted explanation, but did it make sense?
Yeah.
Okay. Okay.
Because she went above.
There's another fly.
Where did it was inside?
Okay, so yes, we divided. It said the marathoner ran 26.2 miles in 2.2 hours. So if you divide that, it gives you 11.9 miles per hour. Oh no, we this is number 14. Sorry, we jumped problems while y'all were sharpening pencils. Good. Yay!
We do. 37. How do you show that at least twice?
How do you what?
Let me show that at least twice.
So it would be an explanation type thing more than anything else. And the most real analogy.
You had to go to 11 to get to 11.9.
Right. As you stopped running, you had to also go 11 miles per hour. Those are more reasoning problems to see, do you understand the mean value theorem? All right, here we go. So 37, the derivative is 1 over x plus 2. And the point is negative 1, 3. So here we go. The domain restriction is due to this being a natural log whenever we find the antiderivative. But let's find the antiderivative. Plus c. That's right. Don't ever forget that plus c. So maybe I'm confused. I'm not sure. I think this is an ln problem. I'm not 100% sure. I could take the derivative here and make sure that I come back to right. They'll use integrals, not antiderivatives. But yes, you could. You could. All right. Y'all are so mean. It's her birthday. Leave her alone. What is the natural log of 1? 0. And so c must be 3. E to the what power gives you 1? The only thing I can raise it to get 1 is 0. Anytime you have a log, any log, even if it's log base, whatever, if this number is 1, it always equals 0.
So ln is the same.
It's ln is log base. What I'm getting at is log of 1 is 0. Log base 2 of 1 is 0. Log base van of 1 is 0. Natural log of 1 is 0. It doesn't matter what this value is. If this is 1, it equals 0.
Very easy and flat. You don't have to like calculate it. The mental math thing.
I feel like we went over log properties in here.
The only thing I know is you do 1 over it and you can do e. So like log of x plus 2, you could write that as x plus 2.
There are only, what?
You could write log x plus 2 as e to x plus 2, right?
No, logs equal exponents. So it would be e to something equals x plus 2. So the two big concepts with logs that are what we use to really work with logs. Changing forms from logarithmic to exponential. And then there are 3 properties, so maybe I will just give them to you real quick because y'all asked about them. Yeah, you need to know how to use them, yeah.
I know that's log base b plus x. Yeah. Yeah. I didn't know that.
That's a minus. No, we're not. There's your 3 properties when we're condensing or expanding that you need to know. Change a base. So if you're plugging in your calculator, so I guess I lied. It was log base b of a. You could plug in as log of a divided by log of b, and there could be any base here. It could be natural log of a. It's just change a base. It lets you evaluate any log in any base. That was a an entire chapter in Algebra 2 we did. I can't believe y'all don't remember.
We did right here.
Mm-hmm.
We probably didn't get to we didn't get to
What? Yeah. Was that me?
Yeah.
I tried so hard to make it meaningful. It was so hard, y'all.
Was it the thing where we had 1 week of work and 1 week off?
Yes.
Oh, I
That was
love
so
that.
nice.
Do that again.
No, look at the mess we're in now because of it. All right. I'm going to give you just a break in between real quick before we start the new stuff. Done first derivative test. We just didn't call it a first derivative test, but it's what you were doing.
What is this called?
First and second derivative. We're just starting notes. We haven't gone over homework. Well, it's
Anti-derivatives, but like after you do the anti, you go back to the.
we're not even. We're gonna take a break from antiderivatives for just a while.
Wow, there we go.
All right. I want you to think about something with me for just a minute. I'm gonna draw a graph on here. Tell me what you know. If this is f of x, so this is my function. Tell me what you know about the derivative at certain places here. Okay. So here, the derivative is 0. Because it's here, the derivative is 0. And here. And a little spot on it. What else do you know about the derivative?
Wait, no, it's going to be for the 4. Yeah, they're saying the derivative.
What else do you know about the derivative? How about this? What do you know about the derivative here? Okay. So, well, the function is increasing, so the derivative, it is. The derivative is positive. That's exactly right. From here to here, right? Because as it goes, and this is the point where it's 0, and that's the point where it changes. So from here to here, what's the derivative doing? And then here, the derivative is, and here, and then again. And that's exactly what we've been doing, right? We've been doing these sign charts, and we find every place where it's 0. And then we look at the derivative, and we say, well, the derivative here is positive, negative, positive, negative, positive. And so we know the function is increasing, right? Everybody agree with that? Everybody okay there?
I just got a good term.
Okay, so first derivative test is just finding these critical points, doing a sign analysis the same way we've been doing, just like this, where this is our derivative and this is our function. Nothing new there. Everybody okay?
I feel like when my kids go to school, eventually they're gonna be like prehistoric. If your kids go to school. Like these are gonna be treated like feathers. You know what I'm saying? I'm not totally doing. Like one day we're just gonna use our hands and stuff.
Second derivative. All right, first derivative tells us maxes and mins increasing, decreasing. Yes, we all agree with that. But the second derivative tells us something very important too. I want you to look at this graph that I've drawn here. And I want to talk about concavity for just a minute. What does concavity mean? Concaves, right? So it talks about we can be concave up.
Can I step out real quick?
You can be concave up or you can be concave down, okay? So kind of like concave and convex, but we just do concave in calculus. And we say it's either concave down. Okay, so if you look at this, concave down, right? But concave up here. What's the point at which this concavity changes? Not at the zero. That's because it's when that slope. You're exactly right, though. Okay, so y'all are getting there. You're getting dangerously close.
Right.
All right. This is called a point of inflection. That's a good job. We'll call it a POI from here on out. That's exactly right. It's stopping the steepness of it. It's changing there. So I'm talking about slopes changing.
Y is no X, because another X is one number.
You're getting there. Okay, but it's not changing from positive to negative because the slope's not changing signs. But let's think about it.
Doing like there's a line through A and B.
If we divide it, we could divide it there. I'm gonna just throw it. I'm gonna just tell you. Okay, I'm gonna just tell you because we could go through and graph this first derivative and then I could show you what happens. But I'm gonna just tell you. Point of inflections happen when the second derivative is 0. So when the slope of the tangents are horizontal. Okay, is that Dylan yelling out there?
Wait, so the slope of the tangent means the I route here.
Okay, now this is the slope of the slope. It's going into 6. So what we'll do is we will also have that on here, and it will tell us about the concavity of the graph. Okay. We are concave up when the first derivative is positive, and we are concave down when the first derivative is negative. So also on my chart here, I'm going to add another line to my sign analysis, and it's going to have these points of inflection. So it's going to be the second derivative and what it does to the graph. So I'd have my points of inflection. Something like that. This is we're getting ready to start curve sketching is why. Can you put it what? Yeah, because I started writing on it. Let me just finish this one and then I will. All right, so this one will be, and we're going to do this algebraically, so you'll see. But I just want to show you briefly what a sign analysis would look like on something like this. Is it what? Yeah, because see how I lined up the maxes and mins on the first derivative graph and the points of inflection on the second derivative graph?
How was that first point, like the first one on the initial graph of point of inflection?
Yeah. Point of inflection doesn't have no, remember it's halfway between.
It always has to be between 2 points?
Yeah, if it's symmetrical, yes. But we're going to actually find it. Go ahead, Noah.
where the arrow is, she could find another one.
I'm talking about.
Yeah, so on the left, she could have like continued going where the arrow should go.
All right, let's do this.
Like, can you give me a rundown?
Well,
Give me a rundown about second derivative.
Yeah,
I accidentally scheduled my flight for.
where the second derivative equals 0, the concavity of the original function changes.
How do you know where it is?
You have to find it and set it equal to 0 and solve it. Okay? That happens those are called points of inflection. That's where concavity changes. When the second derivative is positive, I am concave up. When the second derivative is negative, I am concave down. Okay, so first derivative tells me increasing, decreasing, maxes and mins. Second derivative tells me concave up, concave down, and points of inflection. That's the gist of it. You plug into the second derivative that you found. We're going to do several examples of this. Right now, I just want you to know what it does before we start working on it. Yeah. Okay.
I don't know why I was thinking. That's why I said this is completely unrelated.
Now, let me say this also. This you have to kind of think about, okay? Think about the way derivatives are, okay? What might be happening on the graph of the derivative that indicates a point of inflection on the original graph? It does. Well, yeah. And what happens at change of direction points?
Signs change.
But what is it called? It's a max or a min, right? So a max or a min on the derivative, right? A max or a min on the derivative is going to be a point of inflection on f of x. Because the max or mins of the derivative is where the second derivative equals 0, right? I'm just taking in another step. Does that make sense? Yes. Yes. And this is where we really get into calculus-y stuff. It's my word. I like these. These are fun to me once we get into them, but they are difficult to grasp. We will spend several days on this, working through this.
I'm glad it's
Can we take a field trip to McDonald's? I'm really hungry. Why McDonald's?
Okay.
Close. We don't want to lose too much class time together. Yeah, that's true. We can go to Wendy's.
Have y'all eaten any Popeyes?
Like Wendy's is overrated.
I didn't even know that. Okay.
It's not the chicken. It is so good. I don't.
All right, I'm gonna give you this little theorem here, and then we're gonna work several problems. If the derivative is 0, okay, the derivative is 0. So what am I looking at here?
When the derivative is 0, you're looking at a max or a min on the second derivative, or wait, no.
Okay.
No. When the derivative is equal to 0,
When
that
the-
means it's a point of inflection on the second derivative.
That's a max or min
On the function, on the original function, right. It's what we've been doing the whole time. But now I'm going to add that if you have the derivative equal to 0, and the second derivative, remember how we've been plugging in to find out, is it a max, is it a min, was it big or small? But if also the second derivative is negative, so that means what's my concavity look like? I'm concave down. So if I'm concave down and I have a max or a min, then what is that point? Is it a maximum or a minimum? It's got to be a max. We're going to call it local because we don't know what else is going on in the graph. But for this area, if the derivative is 0 and the second derivative is negative, then f of c is a local max. It is a max. It is a max. If it's concave down, it does this.
Concave down.
No, that's concave up. That's when the second derivative is 0. If the second derivative is negative, it tells me that I'm concave down on that area. Then f of c. So at this point, if my first derivative is 0, no, I didn't. Yes, I did. I'm getting excited. All right, so then the converse of that is also true. Let's see. Well, not the converse. That's not converse. Okay, if the derivative is 0 and the second derivative is positive, what do I know?
It's a min.
Then it's a minimum. Y'all are getting it. All right, let's do a couple examples. This is going to quickly become, what you'll be doing is you could be given the graph of the first derivative and asked to graph the original function, or you could be given the graph of the second derivative even and asked to go backwards. We go a little from Calc 1 in college. Okay, so Calculus 1 in college is essentially the Algebra 1 of high school. It's the equivalent of, it's like the intro math class in a regular 4-year college. This probably takes you, AB probably takes you through Calc 1 and part of Calc 2.
Yeah.
Yeah. And I say that because when I took AP, when I did, and I mean, it's been a lot of years ago, but I think I told y'all that story. I saved my AP Calculus notebook, and it got me through, well, I exempted out of Calc 1, but then it got me through Calc 2 also. Yeah, you could. A lot of people last year, a lot of the ones in AP Calc, even if they passed the AP exam, they retook Calc this year because it was a GPA booster form in college. Right. And it was in solid, especially depending on your major. All right. Yay, nay, maybe so. Let's see an example. We're just getting our feet wet right now. We will do a lot more with this soon. Let's do the first derivative test first, and then we'll do some second derivative tests. You only have, yeah. It's just 1 through 12, and I'm going to start doing them with you right now.
What's the homework called at least? Could you tell me that?
First and second.
First, second derivative. Page 229, 1 through.
Why did we not write
1 through 12. We'll do 1 through 12.
Oh my gosh, stop. Wait, what's the page?
Page 229.
Oh, yeah.
I really wanted to throw a couple more in there, but.
Oh, that's fine. What?
Let's do 1 through 12 and 21 through 24, because that's with the graph. That's going to help you. 1 through 12 and 21 through 24. 21 through 24 are looking at the graphs and telling this is the homework. All right. Yes, let's do one from each section to make sure you understand. So you want to do number 1?
I guess.
Number 1, y equals x squared minus x minus 1. And it says to use the first derivative test to determine the local extreme values of the function and identify any absolute extrema. So put your answer graph. Yes. Well. All right, how can I use the first derivative test? What do I do first?
All right, you're going to take the first
Find the first derivative. If I'm going to, that's exactly, you're right. All right, so first derivative is Whoa! 2x minus 1. You just jumped ahead. That's right. Set it equal to 0. And solve. So the first derivative test is exactly what we've been doing for extreme values. We take our function. We're going to look at the first derivative and tell what it does to the function itself. 1/2 is my point in question. We are. Should I, as I look for the sign, am I plugging into the original or the derivative? I'm plugging into the derivative because I'm looking for the bottom first. So I'm looking for the sign of the derivative because that will tell me what the function itself is doing. All right. To find that value, yes, but to find if it's positive or negative for increasing, decreasing. So if I use 0 here,
I'm right. That's why is it? Wait.
plug 0 into the derivative.
No, I thought we plugged in 1/2.
All right. Here's 1/2. I plugged in 0 into the derivative because this is looking at the derivative.
You're checking like the whole thing.
Right. So my function is decreasing from -infinity to 1/2, yes?
Yeah, so 1/2 is either a max or a min.
Well, we're fixing to see.
It's going to be looks like some min.
If I plugged 1 in, maybe. 2 minus 1 is 1. It's positive. It's going up. Okay. So before I even do that, let's think about this. Does this make sense, taking your knowledge of what this graph would look like? It should be a parabola opening up, right?
AKA.
So this is not part of the problem, but Van, you're exactly right. If I found the second derivative here, I'm always concave up on a parabola that opens up, right? So my second derivative should always be what? Positive. I shouldn't have any zeros because it never changes concavity. What's the second derivative? 2. 2 is always positive. That means it's always, and again, it didn't ask you to do second derivative. You can't because it's never going to be 0, and that makes sense because there are no points of inflection. It never changes concavity, so I shouldn't have any zeros because it's a parabola that opens up. It's always concave up.
Because it never changes direction or it's never 0.
You would. For a cubic, you'd have 3x squared, and then whatever you'd have just x, so you'd have 1 0. And that makes sense because you'd have 1 for a cubic. You have 1 point of inflection. You go from concave up to down 1 time.
So basically, all you can say for this is that 1/2 is an absolute.
So 1/2 is the absolute minimum. You need the function value at that point. So you would do f of 1/2 to find that function value. Yes.
So second derivative is 0. That's right.
Yes. That's exactly right. Good job. If you plug this in, you should get -5/4, I think.
Plug that into what?
Let's see.
You plug that into
The function itself. Remember, we're doing all this with the derivative, but we're using it to evaluate the function itself.
1/2 squared is 1/4. 1/4 minus 1/2.
Right. So we know it's an absolute because of the end behavior here. So the absolute minimum occurs at the point 1/2 -5/4.
That is not
That's what? No, that's 1 through 6 is like this.
So why is the
Yes.
graph A?
That is not what the graph looks like. That.
It's not. I was just, and you don't even have to do any of this. I was just digressing to make sure you understood that.
All right, let's do like 7. No, actually, can we do 6 first? Yeah, let's do 6 then.
All right, number 6. That is correct. This one, if I plug in 0, this one I'm sure is going to be differentiable. This is going to be a piece of a parabola going down and a piece of a parabola coming up. If I plug 0 in, is it not continuous?
When you plug in 0 to that,
It's not continuous.
But
Yeah.
you can only plug it into the second one, right? You can only plug 0 into the second one because the first one has to be less than 0.
So what we'll do is we'll treat these two separate ways because it could still have max or mins even if it's not continuous. So we'll just evaluate separately and we'll look at these points as being potential critical points and we'll see what the function itself does from it. For it to be, yes, continuous,
you're saying the
yes,
same
and
number,
different,
same
yeah,
number from both.
right, right.
Well,
Is that what they did?
I mean, it's not really what's asking. It's not asking if it's continuous or differentiable.
They what? Yeah, that was what I would do.
Because it's not asking us about.
Right, but it's not. It's not. No, I would argue on this one that it's not differentiable because it's not differentiable at the point 0 because it's not continuous at 0. But we can still look at it. If we think about graphically what this looks like, smaller than 0, so it starts at 0 if I plug in the 0, 3 with open dot, but then it goes left. So at -1 would be 3 minus 1 would be 2. And this is a parabola that opens down, so it does something like that. Mm-hmm. Top. I made it an open. Mm-hmm. No, you're not. Stop. Then this one I'm going to do 0, 1. And then 1, 2. So this is what my graph looks like.
So that is not
It's not continuous.
differentiable, aka not you're trying to find max and min, but if it's not continuous, how could that be a max?
There really isn't a max or a min. Well, there's a min for the second one. Well, no, there's a max for the first one.
I would say this is a local min for that piece.
Speaking of local min,
What does the answer say?
I don't know. What's the answer say? Does it say 0, 1 as a minimum? Blah. I don't agree with this one. So we always test the point that is the point, this point. We always use that as a potential critical point, right? So if you let that be, if you put that on your sign chart, when I'm less than 0, my derivative is positive.
Well, let's put in -1. No, it's positive. Yeah, it's positive.
So if you plug a negative, -2x, a negative times a negative is always a positive. So it's always going to be positive, right? What? Because I'm on this side of the 0. So anything on that side of the 0 is negative. And now for this one, if I plug in a positive, it's always positive also. Yes. Well, I disagree. It's not, you can't justify maximum because the derivative is not changing signs here. I don't agree with your book on this one. I'm going to say that this is not differentiable at 0, so we can't call it. leave that one. I don't agree with that. Leave that one and we'll come back to it. Put a pin in that one. Let's do the concavity test. Let's do number 7. Is 7 through 12 what? Yeah.
So basically, we need to get the second derivative.
All right. So yes, it says use the concavity test. Concavity test is just the second derivative test. Use the concavity test to determine the intervals on which the function is concave up and concave down. So same exact thing I've done with the first derivative. Find the zeros and find the signs there. The only difference is it's the second derivative instead of the first derivative, so you should do it twice. I don't think so. If you do the first derivative, you got 12x squared plus 42x plus 36. If you do the second derivative, you have 24x plus 42. That is correct.
Oh, it's the second derivative.
I can look at the answer in the book and see. 7 over 4. Correct. Use the concavity test to determine what intervals were concave up and what intervals were concave down. So this is second derivative. I always find it helpful to label second and derivative and first so that I don't get confused on what I'm plugging into and what it's determining. So again, back to the second derivative. So I'm looking at this.
Wait. Can I ask a question?
You may. Second derivative.
No, but the one above it. Wouldn't that?
No, because I want to know what the function itself is doing. Not what the derivative is doing, but what the function itself
You're
is
using
doing.
a test to figure out what the function is.
That's correct.
So are we just going to plug values into the second derivative?
Yep.
Right, let's go ahead and, so, yeah, plug in negative 2.
What happens?
We don't know, we're asking. Well, we know
Negative
that
48 plus 42.
Wait, so you plug in negative 2 to the second derivative, right?
That's correct.
Negative 48 plus 42.
Zero's easy. Gives me what? Positive. Concave up.
So it's a maximum.
So concave up is going to be on the interval what?
Negative 2, negative 7.
Negative 7 over 4 infinity. And concave down is going to be negative infinity, negative 7.
Oh, that was concave up. So I was reading it back.
That's what I was saying.
My fault. I don't understand why you.
I just wrote it backwards. I'm sorry.
I meant 7 over 4. Why is it not included?
Well, because.
Never included, just like the first derivative test not included. This is not included.
But the function does.
Yes.
Will you please comment?
Is it home? Is this Friday night? I will try. I'll try.
You haven't come in. Can
We
you
have
come
a-
to one this week? No, you did not. Mr. Gee, no, you didn't.
Okay.
You just be chilling.
I'll just be chilling. All right, let's do 21 and then I'll be done. Is it 9:50 or 9:55?
Look what I have to watch the whole day in this time.
You're leaving? They're not home. Why are you leaving this stuff? No. All right.
Okay, I'm trying to draw this as accurately as possible. This is the graph. Look carefully because 23 and 24 give you the graph of the derivative. This is the graph of the function. 21.
So is that an arrow on just the left?
No, it's not bad.
Well, it's not really that hard to follow the edges, obviously.
First thing I want to know, where is the derivative equal to 0?
I was thinking that. Where's the derivative equal to 0?
How do you know? Maxes and mins. Those are the maxes and mins. Right. And this is just to estimate. We're just looking at the graph and trying to estimate those points. Where is the derivative positive? Estimate those intervals. Where? Why? Because I'm looking at the slope. It looks like, okay. And from 1 to. Where is the derivative negative? Negative 1 to 1. Is anybody confused? Where? What's confused? Remember, derivative, this is the function, so I'm talking about, you have to stop and think about what it is you're looking at, okay? The derivative is the slope, right? This is the function. So when is the slope? Right.
Would it not be the negative one? Like, the derivative is greater than 0 from negative.
Yeah, sorry. I left the negative off, sorry. We said it and I didn't write it. All right, now let's talk about second derivative. Where do you think, and this is going to be an estimate because this is a little hard to tell, but where do you think the second derivative is 0?
I like negative 2. Negative 2. I could say negative 1 and 1/2. Negative 2. I'd say negative.
I agree with Meg. I think there's 1 point of inflection here. How do you know? Meg, tell them how you know. Second derivative tells me about concavity, so where does the concavity change? Well, if it continues in this pattern, it's always concave down. It looks like about halfway between, it's changing from concave down to concave up. It looks like there's just 1 point of, yeah. How we write what? Where is the second derivative bigger than 0? So what am I looking for on the original function?
You're looking for the concave up.
Concave up. Where am I concave up? Do you see how we're using this graph to answer these questions?
It's not really that hard.
No, not on derivatives.
Less than 0 from negative to negative.
Now, when you're given the graph of the original function, it is easy to find these. However, on 23 and 24, you're given the graph of the derivative. Oof.
It's literally telling you when it's going upward.
We figured out? Remember, maxes and mins on the derivative are points of inflection on the function. That is critical. And we've already written that one time, but I'm going to write it one more time. Maxes and mins on the derivative are points of inflection on the function. If I'm looking at the first derivative, okay, the maxes and mins are the points where the second derivative is 0.
Are you saying the graph of the first?
Yes. Yes, because 23 looks very similar to 21, but the end behaviors change, but it's a derivative graph and not a, so my original function is going to be a quartic instead of a cubic. All right, that's